On August 6, 2025, while 3i Atlas was still more than 3 astronomical units from the Sun, astronomers redirected the James Webb Space Telescope to point its near-infrared spectrograph at the incoming object. A spectrograph doesn't just take a picture, it splits the light coming from an object into its component wavelengths, the same way a prism splits sunlight into a rainbow, revealing the specific chemical fingerprints hidden inside that light. What Webb found, in a study led by astronomer Martin Cordner, immediately stood out as unusual. The coma surrounding 3i Atlas was dominated by CARB-2 of the most powerful telescopes ever built, just pointed at the exact same object in the sky, independently, months apart, using completely different methods. And they both came back with the same impossible answer. This thing is not from here. It is not from our solar system. It is not orbiting our sun. It came from somewhere else in the galaxy. It has been traveling for longer than Earth has existed, and it is now the third confirmed object in the history of astronomy to prove that our solar system is not sealed off from the rest of the galaxy the way we once assumed. Its name is 3i Atlas. And before you picture something dangerous, let's get one thing out of the way immediately, because it matters. This object was never a threat to Earth. It never came close enough to matter, and every calculation of its path confirms it is already leaving permanently, never to return. What makes this story worth 40 minutes of 2 of humanity's most advanced telescopes is not danger, it's something stranger. Because when scientists finally broke down what this thing is actually made of, the chemistry didn't match anything that has ever formed in our solar system. Not close. And the leading explanation for why is almost hard to say out loud. This object may have started forming before our sun even existed. This is the story of the third interstellar visitor humanity has ever confirmed, and the 2 very different telescopes that ended up studying the exact same target and walking away with the same extraordinary conclusion. I'm your host, and this is the channel that goes looking for the discoveries other channels rush past. If that's you, subscribe, because there's a lot more of this coming. Let's talk about the 2 telescopes themselves for a moment, because the fact that both of them ended up studying the same object is part of what makes this story remarkable. The Vera C. Rubin Observatory is the newest major astronomical facility on this list, built high in the mountains of Chile and designed around a single, extraordinarily ambitious goal: photograph the entire visible sky, repeatedly, every few nights, for a full decade, building the largest and most detailed time-lapse movie of the universe ever assembled. Its camera is the largest digital camera ever built for astronomy, capable of capturing a field of view large enough to fit dozens of full moons in a single image, all in extraordinary detail. That combination of scale and speed is exactly what's needed to catch something like an interstellar object, a target that's only visible for a few months before it's gone forever, moving too fast and too unpredictably for older, narrower survey telescopes to reliably catch in time. Rubin was still in its commissioning phase, not yet fully operational, when it accidentally captured 3i Atlas in its test data. Once its complete 10-year survey begins in earnest, astronomers expect it to transform the search for interstellar visitors from a rare, lucky accident into something closer to a routine, predictable catch. James Webb, by contrast, isn't built to scan the whole sky. It's built to stare with extraordinary precision at one target at a time, pulling out details no other instrument can match. That's exactly why scientists had to interrupt Webb's regular planned observing schedule to redirect it toward 3i Atlas, a request that had to be specifically approved, because time on Webb is some of the most competitively sought-after resource in modern astronomy. Getting that approval, twice, once before perihelion and once after, shows just how seriously the scientific community treated this object the moment its interstellar origin was confirmed. Let's start with what interstellar object actually means, because this term gets thrown around loosely, and the real definition is stricter than most people realize. Every comet and asteroid that has ever been studied before 2017 was born here. In our solar system orbiting our sun, made from the same original disk of gas and dust that formed the planets 4.5 billion years ago. Even the ones on wild, elongated orbits that take them far out past Neptune are still gravitationally bound to the sun. They came from here, and they're staying here, forever, looping around on some orbit, however long. An interstellar object is different. It arrives on a hyperbolic trajectory, a path with so much extra speed that the sun's gravity can bend its course but can never capture it. It swings through our solar system once, on a path that proves it was never orbiting our star in the first place, and then it leaves, permanently headed back out into the galaxy, never to return. The first confirmed object like this was Oumuamua, spotted in 2017, a strange elongated body that showed almost no comet-like activity at all, which made it deeply puzzling. The second was Borisov, discovered in 2019, which behaved much more like a familiar comet, complete with a visible tail. 3IR Atlas, discovered in the summer of 2025, is the third. And it may turn out to be the most scientifically significant of all three. It was first spotted by the Atlas survey, the same NASA-funded asteroid tracking network the object is named after, on July 1st, 2025. But here's where the story gets its first genuinely strange twist. It turns out Atlas wasn't actually the first telescope to capture this object on camera. The Vera C Rubin Observatory, the newest and most powerful survey telescope ever built, had already photographed 3I Atlas weeks earlier, back on June 21st, during its early commissioning and science verification phase, before the observatory was even fully operational. Nobody noticed at the time because Rubin's automated pipeline for flagging fast-moving solar system objects wasn't running yet. Researchers only found the object buried in that earlier data after Atlas made the official discovery and the world knew what to look for. Scientists who later dug through Rubin's early test images confirmed as much, concluding that had the science validation survey started just slightly sooner, Rubin, not Atlas, might have been the observatory that first welcomed humanity's third confirmed interstellar visitor. Once astronomers knew where to look, Rubin's data turned out to be extraordinarily valuable anyway. Using custom techniques built specifically to squeeze information out of that early commissioning data, researchers used Rubin's observations to make precise position measurements, collect detailed brightness data, nail down the object's exact orbital path, and study the structure of its nucleus and the surrounding coma, the fuzzy cloud of gas and dust that forms around an active comet as it warms near the sun. That coma turned out to be one of the most important details in the entire story because Oumuamua, the very first interstellar object ever found, showed essentially none of it, which is part of why the first visitor stayed such a frustrating mystery. 3I R Atlas was only the second interstellar object ever confirmed to clearly show that kind of cometary activity, meaning astronomers finally had actual gas and dust to study, not just a bare, silent rock tumbling through the dark. Rubin's orbital calculations reveal just how extreme this object's trajectory really is. 3I Atlas arrived on a hyperbolic orbit with an eccentricity of 14, the highest of all three confirmed interstellar objects to date, and carrying roughly 58 kilometers per second of extra speed, the energy that no gravitational interaction inside our solar system could ever explain. That kind of speed is the signature of an object that has been drifting through the galaxy, unattached to any star, for an enormous span of time. It reached its closest point to the Sun, called perihelion, on October 29, 2025, passing at a distance of about 4 astronomical units, just inside the orbit of Mars. Its closest approach to Earth came about 7 weeks later, on December 19, 2025, at a distance of roughly 270 million kilometers. For context, that's nearly twice the distance between the Earth and the Sun. Nowhere close enough to pose any risk whatsoever, and through all of it, the comet survived. Despite early speculation online that the intense heat of perihelion might break the object apart, 3I Atlas came through its closest solar approach fully intact. While Rubin was mapping the object's path and structure, an entirely different telescope was doing something Rubin was never built to do: reading the object's chemistry on dioxide at a ratio of roughly 8 times more carbon dioxide than water, one of the highest such ratios ever measured in any comet, and dramatically higher than what's typical for a comet sitting at that distance from the Sun. Alongside the carbon dioxide, Webb detected water, carbon monoxide, carbonyl sulfide, water ice, and fine dust woven through the coma. The team's cautious interpretation was that the object's nucleus is intrinsically rich in carbon dioxide, possibly because whatever environment its ices formed in exposed them to far more radiation than the ices that built the comets native to our own solar system. And then, after the comet swung past the Sun and started heading back out toward interstellar space in December of 2025, Webb took a second, deeper look. This time, warmed fresh from its closest solar pass, the comet's ancient ice had converted into an even brighter, more active coma of gas, ideal conditions for detailed chemical analysis. This follow-up observation turned up something new: methane, methanol, and ethane, along with something even more valuable to scientists trying to trace the object's history: measurable isotope ratios of carbon and hydrogen, including deuterium, the heavier form of hydrogen that carries an extra neutron in its nucleus. That detail might sound technical, but it's the single most important piece of this entire story, because isotope ratios work like a chemical fingerprint tied to the specific environment an object formed in. Every comet native to our solar system carries isotope signatures shaped by the particular conditions of the young solar nebula that built the planets 4.5 billion years ago. When researchers examined 3I Atlas's ratios, the results didn't match. A paper detailing the findings, published June 22, 2026 in the journal Nature, described chemical ratios of carbon and deuterium that simply are not found in any comet that formed inside our own solar system. Working backward from that chemistry, scientists tried to reconstruct the kind of environment this object must have formed in, and the results surprised even the researchers running the analysis. A separate complementary study using the European Southern Observatory's Very Large Telescope, led by astronomer Cyrielle Opitom, examined the object's carbon and nitrogen isotope ratios through the chemical signature of cyanide, adding another independent layer of evidence pointing toward the same unfamiliar origin. As NASA Goddard's Stephanie Milam, a co-author on the Webb study, put it, finding these rare isotopes is fascinating on its own, but the bigger picture is what it means for understanding the possibilities of prebiotic chemistry elsewhere in the galaxy. Because, as she noted plainly, so far we know of only one place in the vast cosmos where chemical ingredients led to life: our own solar system, our own Earth. Put together, the chemistry from Webb and the orbital data from Rubin tell a single, coherent, and genuinely staggering story. This is not a rock that wandered out of some nearby star system a few million years ago. The isotope evidence, combined with the object's extreme hyperbolic speed, points toward an origin far older and far more distant than either of the two previous interstellar visitors. Some of the analysis built around these findings suggests 3I Atlas may have originated from the galaxy's thick disk, an ancient, slowly rotating population of stars that formed billions of years before our own sun did. If that interpretation holds up, this object's ices could have started forming in a completely different part of the galaxy, under completely different conditions, potentially before our sun had even ignited. An object sitting in our own solar system for a few brief months in late 2025 that may genuinely be older than the star we orbit. That's the real headline hiding underneath the dramatic framing. Not a threat. Not a danger. Something rarer and, honestly, more valuable than either of those things. Physical, chemical proof, sitting right in front of two of our most advanced instruments. That material from other star systems, potentially ancient beyond anything native to our own solar system, genuinely does drift through the galaxy and occasionally pass directly through our neighborhood. To understand why a thick disk origin is such a big deal, it helps to know what that actually means. Our galaxy has a flattened structure most people picture when they think of the Milky Way, called the thin disk, where our own sun and most nearby stars live, formed over the last several billion years from progressively enriched gas and dust. But wrapped around and above that flattened structure is an older, puffier, more slowly rotating population of stars called the thick disk, thought to have formed earlier in the galaxy's history, some of it potentially predating the sun by several billion years. An object built from material in that older population wouldn't just be old. It would carry a genuinely different chemical starting point than anything that ever had the chance to become part of our own solar system, shaped by whatever mix of elements existed in the galaxy at a much earlier point in cosmic history. That's what makes 3I Atlas's isotope signatures so significant. They're not just unusual, they're a plausible chemical window into conditions that existed in the galaxy before our own sun was born. This is exactly why NASA and the European Space Agency have already committed to building the next tool for this exact job. The European Space Agency's Comet Interceptor mission, currently scheduled to launch before the end of this decade, is being designed specifically around the lesson 3I Atlas taught scientists the hard way. Interstellar objects give almost no warning before they arrive, and by the time telescopes on Earth spot them, there's rarely enough time to launch a dedicated spacecraft to go study one up close. Comet Interceptor's solution is to launch early and wait. The spacecraft will park itself at a stable point in space and simply sit there, fueled and ready, until a suitable target, ideally a genuinely pristine comet, or with some luck, a future interstellar visitor, is spotted on an incoming path. Only then will it commit to a course and fly out to meet it directly, potentially giving scientists their first ever up-close spacecraft encounter with material from another star system, rather than studying it only from a distance through a telescope's optics. We've now confirmed this kind of visitor happened 3 separate times in less than a decade. Oumuamua in 2017, Borisov in 2019. 3I Atlas in 2025. And with Rubin Observatory's full sky survey now ramping up, built specifically to catch fast-moving objects like this one far earlier than any previous system could, scientists expect this list to start growing considerably faster. Astronomers involved in 3I Atlas's study have already said as much. This newest, most powerful survey telescope in the world is expected to find many more interstellar visitors once its complete observing program begins. So when 2 of the most sophisticated telescopes humanity has ever built point at the same tiny object crossing through our solar system and come back with matching, independently confirmed conclusions. An ancient chemical fingerprint from Webb, and a precise extreme hyperbolic trajectory from Rubin. That's not a coincidence, and it's not something to be afraid of. It's confirmation. Confirmation that our solar system isn't an isolated island. Material from other stars, possibly from other eras of the galaxy's history entirely, is passing through our neighborhood. And for the first time, we finally have the instruments capable of catching it, reading its chemistry, and understanding exactly where it came from. 3i Atlas is already leaving. By the time you're watching this, it's further away than it was yesterday, and it will keep moving faster and faster back out into the interstellar dark it came from, never to return. It won't be back. But it left something behind that no telescope had ever captured this clearly before. Real, verified proof of what another star system's leftover building blocks actually look like, chemically, up close. If this is the kind of story you come here for, subscribe and turn on notifications, because there's a lot more of the universe passing through our neighborhood than most people realize. Drop a comment telling me which detail in this story caught you most off guard, and share this with someone who needs to know that right now, 2 of our most powerful telescopes just quietly confirmed that something older than our own sun paid our solar system a visit. And we were finally ready to notice.